Welcome to the Explainer. You know, every time you turn on a tap or see a thriving farm, there is an incredible silent engine working tirelessly out of sight. Today, we're shining a light on the hidden underground mechanics of sustainable Tubewell engineering. It is an absolute marvel of physics and fluid dynamics. By the end of our time together, you'll never look at a simple water well the exact same way again. So let's start by asking a critical question. What actually separates a highly sustainable tube well from, well, a completely clogged, useless pipe in the ground? You see, punching a hole in the earth and finding water, that's actually not the hard part. The real engineering challenge, the true test, is keeping the sand out while keeping that crystal clear water flowing at a high volume for decades. The stakes here are incredibly high. Imagine an entire farming community relying on a single well, only to lose their water supply overnight just because of one bad engineering choice down in the dark. Designing a sustainable well requires absolute precision.
Here is the blueprint for today's explainer. 1. Analyzing the aquifer. 2. Mastering strainer design. 3. Selecting the gravel pack. 4. Step-by-step installation. And 5. Preventing well failure. Let's get right to it.
Section 1. Analyzing the aquifer, or, as I like to call it, the math of the dirt.
Before a single pipe is dropped into the ground, engineers have to fundamentally understand the soil they're dealing with. This is called particle size analysis. They use a series of stacked sieves to physically sift and sort the different layers of sand and gravel pulled directly from the aquifer. Imagine shaking a giant sifter, separating the boulders from the pebbles and the pebbles from the fine dust. It's a completely foundational step. If you don't know the precise size of the sand grains floating in your water source, you literally cannot select the right filtration materials. Once that dirt is sorted out, we plot it on a graph to find a very specific metric, the D10, or the effective size. This number represents the grain size where exactly 10% of the sample is finer. Now, you might be wondering, why do we care about the smallest 10%? Well, think of it like bottlenecks in the soil. If the finest 10% of the sand is packed too tightly together, it doesn't matter how big the rest of the rocks are, the water simply can't get through those tiny gaps. This specific metric literally dictates how easily water can move through the underground dirt and into our well. We also use the results from those sieves to find the uniformity coefficient. This is just a simple math ratio, the D60 grain size divided by our D10 effective size. Basically, it tells us how uniform the dirt is. To put that into perspective, think of a jar filled only with identical golf balls. Because they're all uniformly the exact same size, there are huge gaps between them, and water just flows right through instantly. But take that same jar and fill the gaps with sand, pebbles, and fine dust, suddenly the water struggles to push through. That's exactly what this formula measures. Knowing this exact science is the absolute foundation we need before we build our underground filtration engine.
Which brings us to Section 2, Mastering Strainer Design, the true gatekeeper of the well. The strainer, or the screen, is the slotted pipe that lets water in but keeps the sand out. And getting this strainer design right is a massive focus for engineers. It is absolutely not guesswork. The optimal slot size must be strictly designed to retain 40 to 60% of the aquifer sand, specifically targeting that D50 or D60 size we measured just a moment ago. It's a really delicate balancing act. Make the slots too small, you choke the well and get virtually no water. Make them too big, just to let more water in, and you end up pumping a mountain of abrasive sand that will literally destroy your expensive surface pumps in a matter of days. If you do use a larger slot size, you are absolutely required to add coarse shrouding materials on the outside to stop that sand, otherwise your well is going to clog almost immediately. Now, check out that VC variable at the end of this screen dimensions formula. That calculates the required length and diameter of the screen based on entrance velocity. Engineers actually have to physically calculate the surface area of the pipe to perfectly match the volume of water they want to extract. The physical dimensions of the strainer pipe depend strictly on how fast the water is allowed to pass through those microscopic slots.
And the magic number for that entrance velocity? Exactly 0.03 meters per second. This is a crucial, non-negotiable limit. The water must not enter the screen faster than this exact speed. To put that in perspective, 0.03 meters per second is barely a trickle. It's an incredibly slow, gentle crawl. It's basically a strict speed limit for the underground highway. If the water moves faster than this, it creates turbulent flow. That turbulence violently tears sand loose from the earth, drops the water pressure, and dramatically accelerates the buildup of hard mineral crusts on your pipes. Because the speed limit is so incredibly low, engineers often have to use very long strainer pipes just to safely collect enough water.
Moving on to Section 3, Selecting the gravel pack, the VIP line.
Gravel pack selection is another huge focus in Tubewell Engineering. If your aquifer has exceedingly fine sand, your strainer slots alone just won't be enough to keep it out. You need an artificial gravel pack or shrouding. Think of it as a custom-engineered bouncer standing outside the strainer, and the rules for this VIP line are strict. First, the gravel size must be exactly 4 to 6 times larger than the source sand's 70% retained size. Why? Because this specific ratio creates a natural bridging effect, allowing the gravel to interlock perfectly and block the sand without blocking the water. Second, the uniformity coefficient of this gravel has to be 2.5 or less. We want those gravel pieces to be mostly the exact same size so water flows hydrodynamically through them without uneven resistance. And third, you must apply a minimum thickness of 75 millimeters all the way around the screen. This ensures complete, robust coverage without the gravel shifting and leaving a weak spot. Sticking to these precise properties is the absolute secret to successfully retaining fine sand while drastically increasing your overall water yield.
Section 4. Step-by-step installation. Actually building the engine in the dirt.
So, we have our aquifer mapped, our strainer designed, and our gravel carefully selected. First, we have to sink the hole. For shallow wells up to 50 meters deep, engineers often use a manual sludger, or the Dickey method. It's rhythmic, back-breaking physical labor, where a crew manually raises and drops a heavy pipe through a water sump to slowly cut the soil. For deeper wells up to 350 meters, they switch to massive industrial donkey and rotary methods, utilizing aggressive cutting bits, pumped drilling fluids, and loud engine-driven rotary tables. But here's the dramatic catch. Regardless of whether you're using manual labor or heavy industrial machinery, if you strike a massive, impenetrable, dense rock layer halfway down, those techniques become completely useless. You typically have to abandon the site, swallow the cost of a week's worth of work, and start entirely over somewhere else.
Once the hole is finally drilled to the right depth, we follow specific step-by-step assembly properties. You carefully lower the strainers, sand traps, and blind pipes into the darkness, locking them in place with that specifically sized coarse sand filled 10 to 15 meters above the top strainer. Next comes the development phase, and honestly, this is an absolutely brilliant engineering trick. You pump the brand new well at 1.5 times its normal rated capacity. This high-velocity surge rips out all the residual clay and drilling fluids. But more importantly, it stabilizes the surrounding soil. Think of this surging action like shaking a box of cereal. When you shake it, the big pieces rise to the top and the fine crumbs fall away. By intentionally overpumping the well, engineers purposefully collapse the fine dirt, washing it out of the system and naturally arranging the largest, coarsest grains of sand permanently locked directly against the screen. It creates a highly permeable natural shell that maximizes the well's porosity for the rest of its life.
Finally, Section 5. Preventing well failure and the severe consequences of getting it wrong.
What happens if you skip a step, or if the math is wrong? Well, it's the ultimate engineering nightmare. If you pump the well too aggressively, or if your slot sizing in the strainer was miscalculated by even a fraction of a millimeter, you trigger severe sand and silt migration. The powerful suction forces an avalanche of microscopic fine materials to relocate inside the earth, completely choking the area immediately surrounding your screen. It essentially cements the well shut, and the water just stops flowing. And remember that 0.03 meters per second entrance velocity limit we discussed earlier? If you break that precise speed limit, the pressure drops drastically right at the screen. This causes dissolved minerals, like calcium carbonate, to rapidly precipitate out of the water. Think of that hard, white, flaky scale that forms inside a boiling tea kettle. Now imagine that thick, suffocating mineral scale rapidly forming over your expensive equipment hundreds of feet underground, where you literally can't just reach in and scrub it off. Because nearly 2% of all wells choke annually from these severe issues, engineers have had to develop intense rehabilitation methods to fight back. Desanding involves dropping a smaller PVC pipe equipped with a spinning toothed cutter to chew up and extract the blocking sand. If that fails, they use a highly precarious side digging method. They slide a specialized metallic ring hundreds of feet down into the earth to carefully grab the existing PVC pipe. The goal is to slide perfectly around the pipe and pull it up without tearing or shattering the fragile plastic under massive tension. And for thick microbial biofilms that block flow, they blast the underground system with highly concentrated chlorine water to neutralize the bacteria and reverse the yield decline. It's an intense, constant battle of physics, chemistry, and engineering happening deep underground every single day.
We often take it for granted because water doesn't just sit in a pristine, empty underground pool waiting for us. It hides trapped inside solid rock and dense dirt. Coaxing it out cleanly without bringing the mountain down with it is honestly one of humanity's greatest daily magic tricks. So the next time you draw water from the earth, will you picture the meticulously engineered filtration engine working silently beneath your feet? I hope this explainer has given you a profound new appreciation for the incredible science of tube wells.